All right, so this is our chapter 7. We're moving into external flow for convection heat transfer. You remember the game rock, paper, scissors? This chapter is 3. It's not rock, paper, scissors. It's a plate, cylinder, sphere. Oh, there's more, but we're just going to do plate, cylinder, sphere. Didn't we already do plate? Yeah, but we're going to revisit it, and we're going to go back to something that was in fluid mechanics. So we're going to revisit that out of fluid mechanics. And then we're going to build on it. What happens when it's not laminar? Well, it's turbulent, and now you rely on empirical correlations. Because this is a big theme throughout this chapter. When we don't have analytic solutions, we have to rely on experimental measurements, and we curve fit to a model. There are limitations to the use of convection coefficients that come out of empirical correlations, and it's easily plus or minus 25%. Don't be doing convection heat transfer calculations to 8 significant digits. It's just ridiculous. We're going to review a methodology, but sometimes students get lost in how to do convection calculations or using the correlations, so just kind of a review. And then again, the rock, paper, scissors, plates, cylinders, spheres. There's more to this chapter, but we're going to skip it. Okay, an empirical correlation is a correlation that has been promulgated by the king, inferred by experimental measurements, determined by analytic methods, or developed in the English-British system of units. Maybe we should put E as a, if there's not an E, you could always type in an E for IDK, right? Shorthand for I don't know. So you can do that. You can do that. Because I think some people are just typing in whatever they want. We don't have a king. How many people got things? I mean, I'm surprised. There's no king promulgated down here. No king. Basically, I just told you that it's based on experimental measurements. And so when you talk about an empirical correlation, you can look up the word empirical. Basically, that's what it means. It's based on experimental correlations. True? But, okay, come on. There you go. Let's move on. So we go back and we revisit this flow over a flat plate. And those are our 2 equations. What are these equations? What do they represent? What are the restrictions behind these equations? They represent the conservation of mass, also called the continuity equation, and the momentum equation. Basically, it's the x direction momentum equation, only one direction of it. The momentum equation is a vector equation in general. And you can say that this is sum of the mass equal to 0. This equation would be F equals to ma. F equal ma? Really? Yeah, that's it. In fluid mechanics, that's what F equal ma looks like. What is F equal ma from your dynamics? Newton's law, Newton's second law. It says that if I have an imbalance in the forces of my object, what can happen? The object can accelerate, decelerate. I can have a change in the momentum, the linear momentum of the system. Well, as I've written it here, what is this term? That's some sort of forces through viscous shear stresses, forces per unit area. And what can it do? It can slow down or speed up the flow. It can change the linear momentum of the flow. These equations are pretty abstract mathematically, but they're pretty easy to understand, hopefully conceptually. We'd like to solve that. We'd like to solve these 2 coupled PDEs for the problem where x ranges, x is our coordinate system. It's going to start here at the tip and go off to infinity. And y starts at 0 and goes off to infinity. That's our 2 independent spatial variables, x and y. And we're going to have some boundary conditions. What do you think about the fluid coming in at x equal to 0, everywhere x equal to 0? So u, everywhere where x is equal to 0 for all y is equal to u infinity. Known? That's kind of a boundary condition. We're going to also have some condition down here. What would that one be? That would be no slip. So u at any x for y equal to 0 is equal to 0. Also, v. Somebody says, what is this v right here? What is that v right there? It's different than u. What is the v right here? That's our y direction component of the velocity, isn't it? So we have our velocity vector in 2D is ui plus vj. That's what it is. And so v, that's another way of saying this at the no-slip boundary condition, v at x at y equal to 0 is also 0. So we have boundary conditions along the plate. And we have some boundary conditions sort of far away. What would be the boundary conditions far away? U for all x, y goes off to infinity is equal to u infinity. And what about v for all x as y goes off to infinity? Far away, what is v equal to? Is it also equal to u infinity? Which one is it? What is v far away? Y goes off to infinity, way up here. What is v? Zero, that's right. Well, somebody over 100 years ago was given this problem. I think it was a graduate student. He worked this out. This is incredible. Well, before I get to there, let me see if we understand the equations by a few simple true or false. This equation, true or false, answer select A if you think it's true or B if you think it's false, is limited to incompressible fluid. And we show the results. So a lot of us think that it is true that this is restricted to an incompressible substance. And that's true. And that's clear in the continuity equation. All right. If you said, oh, I want this to be, to account for it, you probably put the rho in here and the rho in there, and then that's how you would modify at least the continuity to have for variable density. But if it's incompressible, that means that rho is constant. First one? All right. He wants to do that one. True or false? These equations, as written, are limited to steady-state conditions. And let's show the results. Yeah, they're limited to steady-state conditions. Where's the transient part in here? So the fluid can be accelerating or over all the times. The velocity at a point isn't changing. It's steady state. All right. Do I want to do any more? No. Is it a laminar flow? Yes. You could put a turbulent viscosity and fudge it for turbulent flow, but we don't do that. It's just laminar. And does this equation neglect the free stream pressure gradient? Yeah, it's not in there. There's not this minus 1 over rho, the partial of P infinity, with respect to x. That would have a pressure gradient in the free stream, which would either accelerate or decelerate the flow. But that's not in here. So this is neglected. That's true. All right. Well, here's the solution. So you take the continuity and the momentum. You say, instead of solving two PDEs, I would like to somehow solve one of them using the stream function. Have you seen this term stream function before? Sure, it's in your fluids book. And the game with the stream function is if I could find this particular function psi such that the derivative of psi with respect to y gives me u, and the negative of the derivative of psi with respect to x gives me the v, then life is easy because that instantly satisfies the continuity equation. So now you have satisfied the continuity equation, assuming that the stream function can be found. You then look at this PDE and you say, I don't like this PDE. I'd like to solve an ODE. So move from a partial differential equation to an ordinary differential equation. We've done that before in this class. You've done it before in your other classes. You usually use a similarity variable. There is, Blasius came up with it, or other people before him, the similarity variable which works for this equation. So you have y divided by the square, or times the square root of u infinity over nu x. Whoever did that first was a genius. With that definition of the similarity, the similarity variable, you're looking for a similarity solution of an ODE of f, which is a function of eta, which is defined as the psi divided by the terms as written. So you take the governing momentum equation and you transform the u, you transform the du dx, you transform all of those terms, you do a lot of algebraic manipulation to simplify, and there is my ordinary differential equation. I didn't come up with it, Blasius did. You then have to transform those boundary conditions so that you have one at 0, the derivative at eta equals 0, and the derivative at eta goes off to infinity. Those come from those boundary conditions that we just talked about. Now I have a third order ordinary differential equation, and it's nonlinear. Look at this term. I have an f times a f double prime. Good luck. How are we going to do that? Blasius was great. He did this a long time before computers. Now we would slap that into a computer. Even we would back up and slap the whole thing into a computer. But nonetheless, let's go to the solution. So as a function of eta, numerically you can solve for f, the derivative of f with respect to eta, and this is covered up by this thing, the second derivative. And so you get the solution. And then you say, well, what is important to me is how deep is, or how does the boundary layer grow? Well, u over u infinity, when this term over here is equal to 0.99, isn't that the definition of the thickness of the boundary layer? So you come down here, you look for 0.99, oh, it's somewhere in there, you come across, and eta is equal to 5 at that outer edge of the boundary layer. So then you unravel, you say eta is equal to 5. Well, what is eta equal to? Well, x is that distance of the boundary layer thickness, and boom, you go. You say, oh, analytically, the thickness of the boundary layer is 5 times x times the 1 over the square root of the Reynolds number. Maybe you remember that from your fluids book. I don't know, or fluids class. The other thing of interest is not only just the boundary layer thickness, but what is that wall shear stress? Okay, here it is in equation form, but then we want to calculate that in terms of the similarity variable. It's a group of terms times that second derivative of f with respect to eta evaluated at the surface. You go over here and you pick that off. It's like you really only use this part of the solution and that part of the solution. And you come in, that's a constant 0.332. So the local skin friction coefficient is this shear stress divided by 1/2 rho u infinity squared is equal to twice that, or you put 1/2 c sub f of x is 0.332 times 1 over the square root of the Reynolds number. These are the big conclusions right here and right there. That's what we get. That's as close enough to an analytic solution for our boundary layer. You can now move over to the thermal. You have to think about a dimensionless thermal. This is our energy equation. Look familiar? We just theoretically solved for U and V. So the only unknown is T. There's a dot, dot, dot. What does that mean to you? I skipped a lot of steps. But you basically take that PDE, transform it into a ODE. You need the solution to the previous ordinary differential equation, and you have this Prandtl over 2 grouping of term. This one you take a look at, it's second order in this transformed eta. You have boundary conditions. You go and get the numeric solution, then you say, great, I got a numeric solution, what do I want to do with it? How about getting h? Well, if you want h, I need to get this derivative at the surface. The numeric solution allows me to calculate that derivative of the solution, and hence the h is equal to k dot, dot, dot. And then you recall, let's take both sides of the equation here for h. Let's divide by k, multiply by x. That's the local Nusselt number. That's our definition of Nusselt number, and here's our result. Numerically, from the Blasius solution for the the velocity profile and then put that into the energy equation. This is impressive. But now we say goodbye to analytic solutions to these problems, and we now rely on empirical, what the king dictates. No. What laws Congress passed. No. Empirical means a lot of experimental measurements, and then they look at it and they say, you know, the form of the solution should be something like this. Maybe we should look for the Nusselt number as a constant, Reynolds to a power, Prandtl to another power. And we'll curve fit and find C, M, and N. And that's the game of convection for a lot of historically what it's been. So, summarize, we are able to, from the Blasius solution, get the growth of the boundary layer thickness, get the local as well as the average skin friction coefficient. This is the only one I showed, these two. And come down here, I didn't show it for the heat transfer, thickness of the thermal boundary layer, but we did show this local Nusselt number. Okay. If it's turbulent, you look at the structure, you curve fit, you find, well, in the turbulent region, this is the growth rate of the boundary layer, the momentum boundary layer, and this is the skin friction coefficient. They curve fit or did a lot of calculations. How about for the thermal? Well, once you're well mixed, then the velocity profile and the thermal profile are the same thickness. It's turbulent. So there's kind of an obvious conclusion, but you have to think about it for a while. And then here is the empirical fit for the Nusselt number. We're done with flat plates. We just have sphere, cylinder. But before we get to that, this is a good little section in the textbook. Take a look at how do I approach and solve convection heat transfer problems. One is identify the flow geometry. Some students, unfortunately, will be given a flat plate problem and they'll grab the correlation for flow inside a pipe. They'll grab the correlation for flow over a sphere when they have a flat plate problem. So you recognize the geometry. There's only a few, right, that we're going to analyze in this section. Then you need to look at your fluid. Oh, I have air, I have water, I have glycerin, I have other fluids. And if they're temperature-dependent properties, you need to find the temperature at which to evaluate the properties. Use the film temperature. People are pretty obvious on this. They like the film temperature. I've never seen students stumble on the concept of the film temperature. Right? If I have a hot surface, cold fluid, I need one temperature to evaluate, just average them. Just add them and divide by 2. Use that temperature to evaluate the temperature-dependent properties. Then think about the flow regime. Is it laminar or turbulent? Because usually there's a different set of correlations if it's laminar or turbulent. Check your Reynolds number. And then, am I interested in a local value, like a local convection coefficient or a local heat flux, or an average for the whole surface? Figure out what you want. Some correlations are for local, some for average values. Then select your correct correlation. Then unravel the Nusselt number to get the convection coefficient. Most time people want the H. All right? So it's kind of like have the Prandtl, get the Reynolds, get the correlation, get the Nusselt. Once you have the Nusselt, use it to get the H. Once I have the H, go get the Q. What is the rate of heat transfer? Local flux or local or total heat transfer, like with the area. Now, sometimes the temperatures aren't known, so the student will get stuck right up in here where, how do I get these fluid properties if I'm trying to calculate some of the temperatures, but I need the temperatures in order to evaluate the properties? You guess and iterate. Most time, if you do one iteration, thumbs up, you're already there. You don't need to do 10 and converge. It very quickly converges. It's just a small correction. We did flat plate. We're going to do cylinder. Here, what do we have? Flow past the cylinder. It's grabbed from some reputable, agency, just a general illustration that's out there. You've seen this in all fluid mechanics books, etc. So what's happening here? Do we understand this? Because we're going to add heat transfer on top of it. But I found that a lot of students are a little wishy-washy on the fluids behind it. So I don't have a lot of time. I'm just going to give you a quick overview of what happens for flow across a cylinder. So we have 1, 2, 3, 4, 5. What's increasing from 1 to 5? The flow velocity that approaches a cylinder. Which one has slowest flow? 1. And if you say, oh, I can characterize that not only having a low velocity, but what about the Reynolds number? It's low, right? So it's slowly approaching. Now, before we move into the more complicated, let's just make sure we understand 1. Slowly approaching. What is this line right here that they show us? Oh, no, just a nice little line. No, what does that mean? What does it represent? Streamline. It's going to be steady state. And if a little pack of fluid is dropped right here, a second later it's right there, a couple seconds later, then a couple more, then it goes like that. That same pack of fluid. It's a streamline. All right. Now, if you're interested in flow along a streamline, that little pack of fluid can accelerate, decelerate. It could flow into a region of higher pressure or flow into a region of lower pressure. True? So let's just work through our mind on this. What about the flow velocity as I'm going here to here to here? Is it really changing? Probably not. But when I get really close right in here, or let me do this one. This one is a special case because it splits and goes around, splits and goes around. Tell me a little bit about the flow velocity at that point right there. What do you call that point? Stagnation point. It's stagnation. Now that we know that the velocity went to 0 at that special point, the stagnation point, tell me about the pressure. Compared to the pressure right here, what happened to the pressure as it went to the stagnation point? The pressure went up. It went up. All right. Now let's continue and go around to the top part. The same little fluid packet, let's say it goes to the top, right? It was headed for the middle, now it diverts, goes around to the top. What happened to the velocity as it went from here to here, as it went that way? What happened to the speed of it? Increased. It went faster. How about the pressure? Stayed the same? Down. Went down. Actually, that's the location of the lowest pressure anywhere in the system, on the top and bottom of that cylinder. All right. Now, before I do the backside here, let me ask the question to compare this one with that one. Far in front, far in back. Tell me about the speed of those two. Are they the same? Is the one in the far in the back a lot slower, a lot faster? What is the speed comparison? The same. How about the pressure? Same? Same. They're the same. That's a big step. That one you got to get straight in your mind before I start talking now about what's happening in the backside. All right. Now let's go from here to here. So we're kind of going there, right? At the top, we were fast flow. What do you think about the speed of the flow right at that point? It's kind of like the stagnation point on the front, isn't it? So it's 0, just like the front. So what happened to the velocity the speed as I went around the curve on the backside? Slowed down. It's slowing down. All right, what about the pressure? Where was the pressure? We compare the pressure. Is the pressure right here high compared to the pressure right there? Which pressure? The second one, the one on the backside, right? Isn't that the higher pressure? So you got flow slowing down, moving to a region of high pressure. Let's compare the front half. This flow right here, that was the flow is speeding up, moving into a region of low pressure. That makes sense. Speeding up, moving into a region of low pressure, they call it a favorable pressure gradient. But the other one, slowing down and moving into a region of high pressure, fluid is like a wiggly worm. It wants to escape. It doesn't want to do that. That's an unfavorable pressure gradient. And right now, at very low speeds, low Reynolds number, it'll do it. But if you increase the Reynolds number a little bit, you increase the approach speed a little bit, it won't do it for very long. What will form in the backside, little recirculation region, and because of that unfavorable pressure gradient, the adverse pressure gradient, there'll be a point up here where something happens, down here something happens, and the fluid will kind of go like that, but then you just get this trap, like going in a circle. That's a recirculation region on the backside. This is a point separation, where the flow separates from the body. Oh, it was following it nicely in the front, but in the back, it wants to separate and form these little recirculation regions. Well, tell me a little bit now about the pressure right back here. Do you think the pressure built up to the pressure that's on the front side? Or do you think now I have a difference in pressure between the front, which is high, and the back, which would be lower? This case, the pressure recovered completely. This case, there's not a complete pressure recovery. It's a lower pressure on the back side because of that separation. Why do we have separation? It's not a favorable pressure gradient. The fluid doesn't want to do that. I mean, it's slowing down and moving into a region of high pressure. It wants to not do that. It'll skirt out the sides, slip out. And that's what so as you increase the speed, the Reynolds number goes up. Those vortices, well, basically those recirculation regions will become oscillatory, and they'll pop off, and then you'll have these vortices, and you'll have trailing sheet of vortices being shed off of the backside. Then as you continue to do it, the point of separation continues to move further up, and you can get a very large wake region now. There's maybe not as much structure as there had been. The pressure is really low compared to the high pressure. But then as you continue to really make it go, what happens here, what happens to the point of separation? It is reduced. And the size of the wake region is reduced. Why? Why? Because the flow in the front side in here is, because it's going so fast right in here, it can become turbulent before it separates. And if it's turbulent early on, it will navigate more of a severe curve and follow the sides onto the backside longer before it separates. It's because of the turbulence up in this region that the wake is smaller. Why do we have dimpling on golf balls? Same thing. The dimpling helps trip and make it turbulent so that it makes the wake region in the back smaller, less of a pressure drop, and the ball goes further for the same hit. There you go. Okay. Well, that was nothing to do with heat transfer, but it sets us up. Now you want to add heat transfer on top of that? Not really. But this is unfortunately why this, okay, we already did all of these. Here's one question. I don't think I asked that question. So for low Reynolds number flow over a cylinder or a sphere, it's sometimes called the Reynolds flow or the Bernoulli flow, the Darcy's flow, the Stokes flow, or the Mach flow. And go ahead and input your answer. Everybody in, let's go ahead and stop it and show the results. And the results say that as a class, we are guessing today. Well, it's Stokes flow. It's just a name. Early person who investigated it. They honor him with his name attached to it. Well, here's the, I hate to say it, but this is reality, cookbook. Because when you have empirical correlations, they put together a correlation. They want it easy to use. They don't want to put together a correlation that's hard to use. And the easiest correlation is just a constant, Reynolds to an exponent, Prandtl to an exponent. That usually they agree is about a third and move on. Sometimes it'll change a little bit. So all you have is a C and M to fit to your experimental data. A lot of people have done it for a range of Reynolds number. And they say instead of trying to make a core complicated, look, if you're in this range of Reynolds number, there's your C, there's your M. So this is the simple empirical correlation. If it's in this range, blah, 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 here's your C's, here's your M. Let's take a look at the range of M. What's the minimum M you see in this whole thing? About a third. What's the maximum? About 0.8. And you'll see a lot of 0.8s, a lot of 0.5s, and some 0.3s. But if somebody comes in with a correlation that says, oh yeah, I curve fit and this M is 0.01, you know what I'm going to do? I'm going to say something appears really wrong. Or they come in and say, oh, that's a 2. Really? Okay, well, it doesn't appear right to me. Now, it's less that you can observe about the value of C. It's just a constant. But does the exponent M, there's usually not a whole lot of range to it. What happens if I don't have a cylinder around a long object in cross flow, but I have a square long object in cross flow, and maybe it's oriented this way to help split the flow or not that way? Well, you just look at your calculation. There's a lot of correlations out there. If your Reynolds number falls in this range, here's a C and M that you can use. What happens if I have a hexagon? There you go. How about if I have a thin plate that's perpendicular to the flow? Well, are you interested in the front side or the back side? As long as you're in this range of Reynolds number, somebody's done a lot of work and you can use this correlation. So the textbook has a lot of them. That's the whole thing about make sure you get the right geometry. You understand your geometry to get the right equation. In the textbook, there's a statement. Again, we caution the reader, that's you, not to view any of the foregoing correlations as, well, we'll pronounce that word later. How do you pronounce that word? Sacrosanct. Yeah. All right, what does this mean? Don't trust these correlations. They haven't been verified by others. Or do trust these correlations. They have been verified by others. Or there's a typo in the book and sacrosanct isn't a word and is a typo. Or these correlations have small uncertainty. Or these correlations have large uncertainty. Choose the best option. The correct answer is only C or D, or D or E, right? That's it. The other ones are wrong. But I'm going to have you revote now. We're going to talk about it a little bit. If somebody said, another way to interpret this is when you give the answer for H or Q or whatever you're trying to do, let's say you're giving the answer for H. If you're giving the answer to H, maybe you can get 2 significant figures to the watts per meter squared degree C. If I said, look, you can only get about 2 significant figures to H, does that agree with D or does that agree more with E? Which one? E? I got DEs. DE. I heard somebody say both of them. DE, you take your choice, Professor. Okay, somebody comes in and they say, H, I've got it to 1, 2, 3, 4, 5. And people do on exam. They get it to, you wouldn't believe how many. They get it to 6, 7 significant figures on exam. And it's boxed and prettied up, and there it is. There's my answer. Now, if they get it to this many significant figures, what does that say about H? They know it with a lot of confidence. There is very little uncertainty in their answer for H. So now I go back and I ask a clicker question. This is my clicker question. If H is only 2 significant figures, is that more in agreement with either D or with E? Now you have to select either D or E. If you don't know, select A, fine. All right, we have to stop. I believe if I gave everybody more time, and then if you talk to your neighbors, I believe everybody would get the right answer. But in the interest of moving forward, we just take and we move on, which means some of you, unfortunately, get the bad feeling of not having the right answer. But if you have very few number of significant digits, that means it's large uncertainty. And that's what this whole thing, this means that there's large uncertainties. But now I need to go back and regrade here because I didn't grade that one. Hey, you improved, right?
Wouldn't it be D though, because it says not with sacrosanct? If we caution the reader not to
We caution the not to view any of these correlations as sacrosanct. Maybe the book authors could reword this, but they're cautioning us. These have large uncertainties, which means you can't get numbers to a large number of significant figures. All right. How about the sphere? What did we say? Plate, cylinder, the last of it, the sphere. Well, here it is. Take a look at this correlation. Now they're getting a little more complex, aren't they? First of all, this is the first time you see a constant plus something. If you took the other correlations and you said, oh, the Nusselt is equal to a constant, Reynolds to the m, Prandtl to the 1/3, and you decided to plot it on a Reynolds-Nusselt plot, Nusselt on the y-axis, Reynolds on the x. First of all, because of this power, you'd probably want to take the log of this equation, and you would put the log of the Nusselt on one axis, and you would have equal to, you would have the log log of c plus m log of the Reynolds number. And then put that Prandtl to the 1/3 in there too, Prandtl to the 1/3. Okay, but the whole thing is finally you have y is equal to mx plus b. So if you plotted on the log of the Nusselt versus the log of the Reynolds, this correlation looks like a straight line with the slope m. But then you have this correlation, and it comes in with a constant plus a function of the Reynolds number to some power. I know it looks a little complicated, but that's going to look like it'll be out here and it'll go flat. That's what it looks like. So the other one, that as you continue to go for smaller and smaller Reynolds number, it'll continue to give a smaller and smaller Nusselt number. The other here for a sphere is once you get down, it's just going to return a constant value of the Nusselt number for that correlation. So it's a different structure. The other thing to point out on this is they have this grouping of terms. And that is a red flag. It's just like, okay, that I've seen this before. This is a way of handling temperature-dependent properties when you have mu over mu sub s. First of all, viscosity is a very temperature-dependent property. Calculate the viscosity at T infinity. All properties are calculated at T infinity except mu sub s, which is calculated at the surface temperature. So when you calculate the Reynolds number, calculate it for the free stream temperature if you have to evaluate the fluid properties like density, viscosity, etc. to calculate that Reynolds number. It's the way people correlated their data, so we have to uncorrelate their data to use it, and you have to know how to do that. All right, I'm not saying one is better than the other, but this is not the film temperature. This is a different way of handling temperature-dependent properties. And again, you start to see this where they give you a correlation, then they say, look, you need to check that your Prandtl number is in this range. If not, don't use it. But if it's in this range, good. You can possibly use it. But then check your Reynolds number. Then check this ratio of the viscosity at free stream divided by the viscosity evaluated at the surface temperature. And if it's in between 1 and 3.2, it's good to use. So all of these have to be checked, and then you can use that correlation. All right, we have this problem. Let's see if we can solve it. We have a 20 millimeter diameter sphere made of steel. They give us the thermal conductivity of the steel, the thermal diffusivity, the density of the steel. It's dropped in a large tank of water. The sphere initially is hot and isothermal at 360 Kelvin. It drops until the center temperature is lowered to 320 Kelvin. The water temperature is a large vat, stays at 280 Kelvin. The sphere may be assumed to quickly reach the terminal velocity in the water. So for part A, how are you going to solve for the terminal velocity? Nothing to do with the heat transfer. Free body diagram, A+. And with the free body diagram, I'm going to have a balance of forces such that it's no longer accelerating. The weight of the sphere. They have a buoyancy force. A lot of people would miss that one. And the drag force. Do we have any other forces? Nope. And at the free fall terminal velocity, the sum of those three forces, 2 up, 1 down, must equal to 0. That's exactly it. So now that you have the drag force up plus the buoyancy force up equal to the weight down, the easy one, I'll give you the weight. It's the mass of the sphere times g. You give me the buoyancy and the... No, I'm just joking. Now, let's work together. What is the drag force? Maybe I should have switched it. Put the weight over here. M times G is the weight. What is the drag force? This chart. What is the y-axis? What is the x-axis? And we're interested in a spherical object, so don't ignore the smooth cylinder curve. And as a function of Reynolds number, you get the drag coefficient. Stokes flow is up in this. This is where you have most spheres would fall. You have this little kink down. What do you have that for? That's our separation at high Reynolds number. It's turbulent flow, and so it's able to reduce the wake region, and it'll actually drop your drag coefficient a lot. Do you see the drop in the drag? A lot. So that explains what we just talked about. So you come back and you say, how do I do that? Well, what is C sub D defined as? Force drag divided by 1/2 rho u infinity squared times the frontal area or the projected area or the silhouette area, whatever you call it. And so if I want to, I just have C sub D times 1/2 rho u infinity. You know, I remember this 1/2 rho u infinity squared. He made a big deal of that the other day. What was that 1/2 rho u infinity squared called? Dynamic pressure. That's right. And then you multiply by that frontal area. There you go. Now, let's move on to the buoyancy force. Here's my clicker question. The principle used to calculate the buoyancy force is called Euler's principle, or Bernoulli's principle, or Newton's principle, or Archimedes' principle, or Stokes' principle. Everybody in? Why is this not more correct? I mean, Archimedes? All right, now, what was Archimedes' principle? The buoyancy force is the weight of the water displaced by the object. Isn't that it? I need to say it in words before I put it in an equation. Oh yeah, Archimedes' principle. The weight of the water displaced by the object is the buoyancy force on the object. True? So easy. I don't know why more people don't get an engineering degree. It's so easy, right? So you take the volume of the object, multiply by the density of the object, the metal object, or the density of the fluid that's being displaced by the object. The density of the fluid being displaced. That's the mass of the fluid being displaced. Multiply by G. Isn't that the weight of the fluid displaced? There you go. So now you look at this and you say, this is really easy. All I need to do, this is U infinity. I'm going to put it as a cap. Oh, man. Let me do this. Velocity terminal. And I'm going to put something through that for a volume so that I don't get confused. This weight is our volume rho of the steel. True? Okay. So this V is volume, that V is volume. This V is my terminal velocity. There's only one rub. Somebody says, to get this drag coefficient, that drag coefficient is a function of the Reynolds number, and the Reynolds number is rho terminal velocity diameter divided by mu. So hold it. I have to be able to get the drag coefficient in order to use this equation to get the terminal velocity. But in order to get the drag coefficient, I have to get the Reynolds number. In order to get the Reynolds number, I need the terminal velocity. You ever seen somebody chase their tail, a dog or a cat chase their tail? Maybe cats are too smart. Maybe only dogs do it. I don't know. True? So what you do is, this is one of my favorite slides, if I can pull it up. How many people remember playing on a playground in the prime of their life? They're 10 years old.
Those
Oh, they're too dangerous now? Oh, that's too bad. I'm telling you, this was so crammed on my playgrounds in my youth that it was so fun. I mean, I can remember playing on something like this, a merry-go-round, when it was so little. I would crawl to the interior, and the big kids would push it around. And then a couple years later, I'm the big kid pushing it around. And flying off and all that. Well, how many places are there a kid can hang on? You hang on here, hang on here, hang on there, hang on here. Look how many places you can go, interior, exterior. But you ever remember trying to get on one of them? It'd be always going. You just had to kind of get in the game. Here it is, the same thing. Get in the game. This is flying around in fluids. Oh, I need to get the V, but before I get the V, I need to get the C sub D. Then before I get that, I need to get the RE, but the V needs to be. Pick your poison and jump in. Assume a C sub D. Calculate the V terminal. Get a Reynolds number. Update your C sub D. Do it another time. Don't even need to do it more than once. You're going to be done. The same merry-go-round iteration principle in heat transfer. We haven't got there yet, but you're going to be sitting here and saying, oh, I need to be able to calculate, maybe a temperature. But I need a Nusselt number. Well, I need a Reynolds number. Well, I need a convection coefficient. Then I need the viscosity. Pick one and go. And often what I would do is look for an opening. Like there's a gap here, I'll jump in there. Well, over here, typically, maybe you're better at guessing a C sub D. Let's take a look here. After you solved a few of these problems, do you think somebody starting with a C sub D 20-ish would be a good guess? Not unless they anticipate being in Stokes flow. How about 0.06 or 0.05? Not a good guess for C sub D. How about guess around 0.5, 0.4? It'll quickly converge. Same here. Maybe you say, I have a good idea what H is. Or maybe I have a good idea what temperature is. Maybe I don't have a good idea what the Nusselt or Reynolds number is, or whatever. Just get in the game somewhere. And there you go on the merry-go-round of iteration.